Alright, so the first take of all my science videos usually turns out really bad. So if you actually get to hear this, class, that means I'm on my game today. But we'll see. So here we go, Earth science. Layers of the Earth. That's right, it has layers. I made this meme myself for you in Photoshop, so appreciate it. But yeah, the Earth has layers. It's not the same all the way through, and we're going to learn about them today. So here are our questions of the week. Can you go to the center of the Earth? And what would you find if you did go? Is our planet made of different stuff than other planets? And has our Earth always looked basically the same as how it looks right now? I think these are some pretty good questions, which is why I'm asking them. Okay, but now I have a question for you. And I'm not expecting you to respond because this is a video, but think about it. How do you think they made maps before, like, planes and spaceships and drones could actually see the Earth from high up? Like, just think about that for a second. Right? It would be pretty hard. And like, you can see in these old maps, like, look at how wonky they are. Like, there's pieces that are missing because they just didn't know what was there. Like, look at how huge, look at how huge South America is here compared to how big we sort of know it is now. Like, it was really hard for them to make maps back then and to sort of see how the Earth was looking. And you can think about biases that would have been present in maps, and biases that are still present in maps. Like, I don't know, why is the northern hemisphere always on top? Makes you think. Alright. And that's going to basically lead us into what's called the theory of continental drift. So, until the 1900s, most geologists, which are people who study the Earth and people who study rocks, they thought that the Earth had, more or less looked the same forever. Which makes sense. Like, think about your own lives and my own life. Have you seen any mountains move? Seen any new canyons open up? Any new islands just appearing off the coast of the ocean there? No. And so it makes sense that people thought initially, the Earth probably has looked like this, since the beginning. But then there was a German scientist named Alfred Wegener. I need to check the pronunciation. That might not be how you pronounce his last name. But we're going to go with Wegener. Collected evidence across the world on climate, rocks, and fossils to support his hypothesis of continental drift. He looked at some maps and he noticed, maybe I'll go back to the maps here. He looked at some maps and he kind of noticed that things lined up a little bit, kind of like a puzzle. He's like, you could fit South America into this little notch in Africa here, and then this kind of lines up, and that kind of lines up. And hey, maybe the continents weren't always where they are now. Maybe they were originally together. Maybe they were somewhere else. And that was his hypothesis of continental drift. And you may have heard of Pangaea, which was his name for basically one big supercontinent that had all of our continents smushed together all in one landmass. And there was evidence from climate, some rocks and fossils of where creatures had lived that supported this. But the scientific community rejected his theory back then, but they accept it now. So let's think about that. Well, why? What makes it different now? Well, back then, they couldn't explain, he could not explain how the continents could possibly have moved. Right? They're pretty big, and a lot of the scientists couldn't even imagine forces that would be big enough to move a continent. Like, that's so much stuff that you're moving around. And if you are thinking of the Earth as a solid piece of rock, it doesn't make any sense. But now that we know about plate tectonics, the idea that, okay, well, the Earth isn't solid rock all the way through, and that there's magma, and then there's the crust of the Earth that's kind of on top of the magma, and things can kind of float, and move around. That makes us a lot more willing to believe that, okay, yeah, the continents weren't always where they were. So we're going to look into that. So what's under our feet if the Earth isn't made of a solid ball of rock? Well, first up, there's rocks. There's the crust here. And then we have what's called the mantle, which is sort of a melty rock layer. You can think of it as kind of gooey, like taffy, I think is how the textbook explains it, but like, don't eat it. It's lava. Well, it's magma. We'll get into the distinction in a little bit. We have the outer core, which is like actual liquid. And then we have the inner core, which is solid again. And it's interesting because no, you can't go to the center of the Earth. You would die because it gets very hot. So like a question that a lot of people have is, okay, how do we know that this is what's in the Earth if we can't go there and we can't actually see it? And I like this because it actually links very well into the topic of refraction and how we talked about how light travels at different speeds through different materials. Well, seismic waves, so stuff like earthquakes, and vibrations travel at different speeds through different materials as well, and that's part of what helps scientists understand what our Earth is made of, which, even though we can't actually see it, which is really cool. So we're going into each little detail, because, I mean, that's what this whole PowerPoint is about. It's about the layers, so I should tell you about them, right? Right. The crust is made of rocks. Continental crust is on land. Oceanic crust is underwater. Oceanic crust is actually thinner, but don't worry about magma coming up through the crust there, because it's deep on the ocean floor, and you probably never have to worry about it. This is a thin layer compared to the other layers, and hey, we live on the crust. So if you go outside and you look down, there it is, the Earth's crust. So we're pretty familiar with that. The mantle, so there's the upper and the lower mantle. So some of it is fairly solid, but some of it is melted rock that is soft and it can flow around slowly. Don't eat it. It's magma. The mantle is the world's #1 supplier of magma for volcanoes, and it's about 2,885 kilometers thick. That's the upper and the lower mantle together. So that's a pretty big layer. And just to explain the magma versus lava distinction, if it's in the Earth still, or even if it's in a volcano still, it's magma. As soon as it comes out of the Earth and is on top of the crust, that's when we call it lava. But it's the same hot, melted rock. I was about to say that we all know and love, but it's dangerous. Don't touch it. Okay. The outer core is liquid iron and nickel. Have you ever seen liquid iron and nickel? Probably not. That's because it has to be very hot to melt that kind of stuff. So it is 4,400 to 6,100 degrees Celsius. Incredibly toasty, incredibly hot. And this layer is also over 2,000 kilometers thick. So this part, unlike the mantle, which is kind of melty rock, sort of soft, not quite liquid, this part is like liquid. Now, the inner core is solid iron and nickel. Now, you might be thinking, okay, if it's hotter, shouldn't it be more liquidy? Like, shouldn't it be even more melted? The reason why it's solid, despite being so hot, is that it's under immense pressure. It's so dense. It's like everything, like gravity and like the whole Earth is pushing down on it. And so this part is so dense, under so much pressure, that even though it's so hot, it's still a solid, which is pretty cool. And so this one is about 1,216 kilometers in diameter. And if we scooch ourselves back to here, you can sort of see the comparisons. We have the inner core, the outer core, the mantle, and then the crust is like this little thin light brown stripe. So that's basically what's in the Earth. What about other planets? Obviously, we don't have as detailed of data on other planets because we live on the Earth. But here's a little bit of this is the best graphic I could find. The terrestrial planets, so Mercury, Venus, Earth, the Moon isn't a planet, and Mars, are a lot like Earth. They have that solid core and probably some magma action going on. But then obviously in our solar systems, there are other planets that are not made of rock. They're made of gas, like Jupiter, Neptune, Saturn, etc. And so those are going to look different on the inside. But for Mercury, Venus, Earth, and Mars, there's a question mark for core on the moon. So I'm not sure if people are sure or not. But it's basically the same kind of thing, which is neat. And makes sense, right? Those are planets that are very close to us. It does make sense that they would be a little bit similar. Alright. And I've written for you a lovely metaphor. The Earth is a pizza. The Earth's crust is the toppings on my pizza. Some parts of the crust are thicker, like mushrooms, which are the continental crust, or thinner, like pepperoni, which is the oceanic crust. The mantle is cheese because it's kind of a solid, but it's also kind of a liquid because it's melty. The outer core is the sauce because it's liquid and hot. The inner core is the bottom crust of my pizza because it's a solid and it's underneath everything else. And your assignment for this week, and I apologize to those of you who don't like creative writing, but I'm going to be asking you to write your own metaphor. So you can't use pizza, because I use pizza, and you can't copy me. But I want you to write your own metaphor about the layers of the Earth. I'm not looking for poetry here. I'm looking to see if you kind of understand the differences between them. Alright, so I'm really excited to see what you come up with. You can do it a food, an object, an animal. I don't know how that would work. But it can be anything. I want you to talk about the different parts of it and what parts of the Earth those are equal to. Okay, that's our science video. I think this one turned out